Welcome to lesson 3.2, working with radicals. We're going to start off without using a calculator, evaluate or simplify as much as possible. And then this first question is asking us to find the square root of 81 squared. So if we were to do this old school, squared means we write it out twice. So that's root 81 times root 81. And we learned last lesson that anytime we multiply two radicals that have the same radicands or the same guts, so totally matching guts in there, then our answer is just 81. Another way to think about it would be, we could think about it, it's root 81 times root 81. So you could put them together under one square root sign. And when you do 81 squared, you get 6561. But then when you square root 6561, you end up back at 81. But the trick way of thinking about this is if we have the square, if we are taking the square of a square root, they undo each other. It's like multiplying by 10 and then dividing by 10. If you take 3 times 10 and then divide it by 10, that just equals 3. So when you square root and square something together, they undo each other. So for the second one, the square root of 153 squared, we can just use our trick now, knowing that the square and the square root undo each other, and we get 153. Now this trick only works when we're multiplying. So when we're multiplying square roots, it doesn't work if you have, won't work if have plus or minus inside your square root. Okay. Question 2 says, without using a calculator, simplify the following. Avoid large numbers by using clever ways to simplify each radical. So the key is there, we're going to simplify each radical, and then we're going to look and see if that helps us out at all. So root 21, I can write that as, I'm going to make this bigger. Root 21, I can write it as root 3 times 7, or I could just write it directly as root 3 times root 7. Looking at root 14, I could write that as root 2 times 7, or root 2 root 7, because all the squished together mean multiplies. And then the last one, where it's root 6, I can just write it as root 2 times 3, or root 2 times root 3. And if I've simplified it, and now the way that I can be clever about it is I can say, okay, I have a root 3 here and a root 3 here, so really I have a root 3 squared. And then root 3 squared is just plain old 3, because the square and the square root undo each other. And then might notice that I've got a root 7 and another root 7, so I can write that as root 7 squared, because they're multiplying. And root 7 squared is just 7, and remember, squished together meant they were multiplying. And then that leaves us with root 2 times root 2, which is root 2 squared, or multiplying by 2. And when we multiply that all together, 3 times 7 is 21, times 2 is 42. Okay, for question B, I'm just going to draw a line. Well, that was supposed to turn into a nice straight line. There we go. A line over there. So root 125 times root 20. So still looking for perfect squares. We did that before when we were simplifying things in 3.1. So in 125, I recognize that that's 25, which is one of our perfect squares, times 5. And for 20, I recognize that I could write that as 4 times 5. And the whole reason I'm doing that, so I can write that as root 25 times root 5, and then root 4 times root 5. But the whole reason I went for those squares because I can take the square root of 25 and it turns out to a very nice number, just regular 5. Then I can take the square root of 4 and that also is a very nice number. I'm just going to color code it. And that square root of 4 is 2. And then finally, I can hopefully recognize that I have root times 5 squared. And the whole reason we like root 5 squared is because we're going to be able to write that just as 5. Root 5 squared is just 5. So then I have 10 times 5, and my answer is 50. For question C, root 2, it's going to stay like root 2. Can't simplify it more. Root 6, I'm going to write as root 2 times root 3. 75, I recognize that there's a 25 in it, so 25 times 3, or I can write it as root 25 root 3. So if you can go right to that step, that's cool. If you don't see it yet, it's also okay. So I see that I have root 2 times root 2, so a root 2 squared, which is just 2. I also see I have a root 3 times root 3, so root 3 times root 3, which is root 3 squared. And root 2 squared times root 3 squared is just going to be 2 times 3, because that square and the square root undo each other. Then I have the square root of 25, which just equals 5. And so I end up with 6 times 5, which is 30. Question D. So, root 20. I'm going to write that as root 4 times root 5. Next is root 45. I recognize that's going to have a 9 and a 5, so root 9 times root 5. 29 I can see is 9 times 3, so root 9, root 3. And 48. 48 is going to show up a couple of times. I think it already showed up. 48, if you rate it as 16 times 3, that's way better than 4 times 12. Because 16 is one of those magic perfect squares that come out. So I'm going to write root 48 as root 16 root 3. That's the biggest perfect square we can take out of there. And now we look for things that we can simplify. So root 4, I can just write it as 2. Root 5 times root 5 is going to give me root 5 squared, which will straight up be 5. That's from all the yellows. I have a root 9 and a root 9, so I can write that as times root 9 squared. And the square root just cancel each other out, so we just get plain 9. Blue. I have a root 3 and a root 3, so I can write that as root 3 squared, which just gives me times 3. And then last but not least, I've got root 16, and the square root of 16 is just 4. So when I have all this, I have 2 times 5 is 10. 10 times 9 is 90. And 90 times 12 is 108 plus a 0, so 1080. So all the time we're looking to break down the square. If we're multiplying it all together, we're looking to break it down so that we can find some doubles. Question 3 is something totally different. Question 3 is looking to see if we notice a pattern. So root of 2 to the 5 times 2 to the 5. I could write this as the square root of 2 to the 5 squared. And then hopefully you remember that the square and the square root undo each other. So I would get my final answer as 2 to the 5. Other way of thinking about it, though, is I could write this as the square root of 2 to the 10. So all I've done here is I did my exponent rules on the guts of the square root, and I get 2 to the 10. But 2 to the 10 has to equal 2 to the 5. These two things have to be equal to each other. So if root 2 to the 10 equals sorry, I think I misspoke earlier. If root 2 to the 10 equals 2 to the 5, we're going to take that as fact. We're going to keep looking and see if we notice a pattern. So if I do it the old school way with the exponents, I will add them up because the bases match. So add the exponents. I get root 3 to the 14. But I also could write this as root, 3 to the 7 squared and square root it. The square and the square root undo each other. So it also happens to equal 3 to the 7. So hopefully by this point, you might have noticed that it looks like square rooting a power. We divide the exponent in half. We had 14 and we ended at 7. We took the square root of 2 to the 10 and we ended at 5. And so our rule is going to be The rule is going to be when taking the square root of an exponent, we're going to divide the exponent by 2, or we're going to cut it in half. Cut the exp in half would be another way to think about it. And after we do that, it's going to be and the base stays the same. The base stays the same. So with our new rule, if I'm taking the square root of 5 to the 10, I'm going to keep the base the same, and the exponent is going to be 10 divided by 2, or 5 to the 5. For D, I'm taking the square root of 21 to the exponent 30, so the base stays the same, but the exponent is divided in 2. So that'd be 21 to the 15. Next page. In conclusion, a square root divides a radicand's exponent by 2. Yeah, we read it on the page before. So if we're taking the square root of 10 to the 8, the base stays the same, the exponent is divided by 2, or 10 to the 4. And if you want to go straight to 10 to the 4, that's totally fine. B, we're going to have to do 2 separate steps. I'm going to have to take 2 separate square roots. So first of 5 to the 4, then of 2 to the 6, and then we'll see what we can do with them. So the square root of 5 to the 4, base stays the same, 4 gets chopped in half, so it goes to 2, times base stays the same, 6 gets chopped in half, so it turns into a 3. That would give us 25 times 8, which is the same as 200. In question C, we've got 2 powers underneath our square root, but they're still just multiplied together. So we could write this as root 11 squared times root 2 to the 4. And now we follow the rule. Base stays the same, exponent gets chopped in half. So 2 would become a 1 times base stays the same, exponent gets chopped in half, so 4 turns into a 2. So we'd get 11 times 4, which is 44. There is no rule for addition under a radical. So whenever we have a plus or minus, so it's addition or subtraction, should have said, or subtraction. There is no rule for addition or subtraction under a radical. We just have to figure it out. Just figure out the guts and then simplify if you can. So for this example, the square root of 4 plus 16, we might be tempted to square root 4 and square root 16, but don't do it. This plus makes it kind of yucky. So that would turn it into the square root of 20. Now there is a perfect square hiding inside there, so I could write it as root 4 times 5, which would give me root 4, root 5, or 2 root 5. And that's what we have to do if we have a plus or a minus. So for 5a, the square root of 3 squared plus 4 squared, because of this plus, means we have to figure out the whole guts first. So 3 squared is 9, 4 squared is 16. So now it's got me taking the square root of 25, and hey, 25 is a perfect square, so my answer is just 5. C looks like it's a lot like A. 3 squared, so 9, plus 16, plus 12 squared. 12 squared is 144. And if we add those all together, we get 169, which also has to be a perfect square. The square root of 169 is 13. Question B. This time we have to subtract. So we're dealing with all the guts together. Subtract them first. So 150 subtract 29 is going to be 121. Again, a nice perfect square. So our answer is 11. For D, we've got two separate square roots with two separate guts. So we're going to have to follow, I should have used a different color, BEDMAS underneath each one. So inside the first square root, it's kind of like brackets. Inside that first square root, 2 to the 3 is 8, plus 1 to the 3 is 1. So my first square root is root 9, which also happens to be 3. And that whole thing then is minus this next one. 6 squared is 36 minus 5 times 4, because we got to follow BEDMAS. So inside here we are following BEDMAS, which gives me the square root of 36 minus 20, which is the square root of 16. So the square root of 16, we actually can do that one. The square root of 16 is 4. So 3 minus 4 is minus 1. And that's it for lesson 3.2. Thanks for watching.